Hello, this is the second part of moment distribution method. Here we have an example, as you can see in the figure. A, B, C, D, a continuous beam. Here A support is fixed supported and all the other support are hinged. Here in every span we can see there are 2-point load and a uniformly distributed load applied here, and same for all the spans. Here we have 3 spans, that is we have AB and BA member, BC and CB member, CD and DC member. Basically AB and BA member are same member, but moment at this point and moment at this point will not be same. That's why we are calling it AB and BA. At the same time we can see the variation in moment of inertia. At this span moment of inertia is 3I. Here I is any arbitrary value, and moment of inertia of this span is 4I, and moment of inertia of this span is twice I. And all the distances are given here, as we can see: 2 meter, 3 meter, 2 meter, 3 meter, 4 meter. From these distances we will get the span length, that is L for different span, and we will use it for our moment calculation and stiffness calculation or further calculation. Okay, at first we need to find or we need to calculate the fixed end moments. Here there will be a fixed end moments in this direction, because due to this applied load, since this support is fixed, there will be no rotation, that is the slope will be 0. To maintain a 0 slope, if we can see if you want to see the elastic curve, the elastic curve of this section will be this. That means slope at this point is 0, and to maintain 0 slope at this point, a moment will create in this direction, and this moment is moment AB. We are calling it fixed end moment, and it is moment AB. What will be the value of moment AB? Here we will get moment for this point load, and this uniformly distributed load. For this point load, the moment will be, as we know the formula, P AB square by L square, 75 into this distance A, where here A is 2 meter, that is 2 into, and this distance is, that is support distance from right support, 5 meter. PAB square by L square, where L is the span of span length of this span, which is 2 plus 3 plus 2, that is 5 plus 2, 7 square. This is the moment for only this point load, and for this point load of 65 kilonewton we will get moment like 65 into this distance 3 plus 2, 5 into 2 square divided by 7 square. At the same time, moment will arise for this uniformly distributed load, which is 20 kilonewton per meter, and moment for this load will be omega L square by 12, that is 20 into, here L value is 7, omega L square by 12. If we sum all this value, then we get the moment for AB member, that is for at this point, and it will be 184.73 kilonewton meter. Similarly, moment at this point, it will be in this direction, and this value and moment of this value will be, and value of this moment MBA, it will be 20 into 7 square by 12, that is omega L square by 12, plus 75 into 2 square into 5 by 7 square, plus 65 into 5 into 2 square by 7 square, and this value will be 178.6 kilonewton meter. Here we need to consider a direction as positive. Here we see that this moment is in anti-clockwise direction, and this moment is clockwise, in clockwise direction. So if we consider anti-clockwise direction as positive, here in this example we are considering anti-clockwise direction as positive, that is this moment will be positive and this MBA moment will be negative, since it is acting in clockwise direction. MBA moment is acting in clockwise direction, that's why it will be negative, 178.6 kilonewton meter. In the same manner, we can find moment at this point, which is MBC, at this point, which is MCB, this point, which is moment MCD, and at this point which is moment MDC. And we should put all the moments value in a table, then it will be easier, it will be convenient for us to solve this problem. So let us make a table. First of all, let's see how many joints are there. Joint, here we have A, B, C, D. It is 4 joint. Joint A, B, C. We have 4 joint A, B, C, D. Now see the member. In joint A we have only one member, that is AB, and in joint B we have 2 members, BA and BC. That is, we need to make another column here, BA and BC. As well as in C member we can see, in C joint we can see there are 2 members, CB and CD. That is, we also need to make an additional column here, which is CB and CD. And for D joint, here we have moment, we have only a single member, which is DC. Now find the stiffness. We know the stiffness K equal to 4EI by L. And what will be the stiffness for this member AB? That is KAB. KAB, it will be equal to KBA. Because both are same member, we now putting on the values of EI, 4EI. Here I equal to 3I by L. Span of this span length of this span is 2 plus 3, 5 plus 2, 7. That is 7. From here we get 1.71 EI. So we can write here 1.71 EI. Similarly, BA is also 1.71 EI. Sometimes we can eliminate EI value, because we will see that in the calculation of distribution factor, this EI will be eliminated. Okay, let's see others values. For BC, what will be the stiffness? For BC member, stiffness will be 4EI. Here I equal to 4I by L, and here span length is 8. That is, we get 2EI. Here 2EI, BC and CV same member, 2EI. And for CD member we have the stiffness. If you want the stiffness of CD member, that is 4EI. Here I equal to twice I by L. Again here L equal to 6, 1.33 EI. 1.33 EI. Here 1.33 EI. Now the distribution factor. What is the distribution factor of a B member? Here we have one joint and one member. Let's see what is the support of this point. At this point the support is fixed support, and at fixed support distribution factor equal to 0, because we assume here all the moment will be carried by support, no moment will be distributed to this member. That's why distribution factor at fixed support equal to 0. And at B joint we have 2 member, B and BC. One member has stiffness 1.71 EI and another member has 1.21 EI. Then the distribution factor for BA will be 1.71 EI divided by 1.71 EI plus 2 EI. Here we consider these two stiffness, because at this 2 point these two members are dealing with. And calculating this equation we will get, again we can see the EI value is eliminated here. That's why we can write this row with eliminating EI, 0.46. Similarly, if we calculate, then you will get the distribution factor here 0.54. Similarly, distribution factor at this member will be for CB member, it will be 2 divided by 2 plus 1.33, because EI is already eliminated here. 2 by 2 plus 1.33. Here it is 0.6, thus it is 0.6, and it will be 0.4. And distribution factor at this exterior joint, at the exterior joint, when the support is hinged, then the distribution factor is 1.00. That is, no moment will be carried by the support, because hinge support cannot carry any moment. All the moments will be carried by this member. We can say hinge support is just opposite to fixed support. For fixed support, distribution factor is 0, and for hinge support, distribution factor is 1. Now we have all the parameters to analyze this structure or analyze this beam. Now write the fixed end moment. We have just calculated a few minutes ago. What will be the fixed end moments? We have calculated fixed end moments for this AB member, and it was 184.73, and for this member we got a negative value, that is negative 178.6, and for this member, that is BC, we got 210.4 minus 199.1, 148.9 minus 137.8. Here pay attention here, one moment is positive, then the next moment is negative, positive negative, positive negative, because one moment is in anti-clockwise direction, then the next moment is in clockwise direction, clockwise anti-clockwise, clockwise anti-clockwise. Here we considered anti-clockwise direction as positive, then clockwise direction will be negative. Anyway, we have got these moments considering fixed support at all the point, and at the same time we can see that at joint B and at joint C we have some unbalanced moment, minus 178.6 plus 210.4. These two moments should be equal and opposite in sign, because summation of these two moments should be 0, because there should not be any unbalanced moment, because these supports are hinge support. At any hinge support, this moment and this moment should be equal, because these two moments will be balanced by each other. Now this is our fixed end moment. Now we need to distribute this moment using moment distribution method. The application of moment distribution method is just here. First of all, we need to balance this moment, and we call it balanced moment. At this point, at joint A, we have moment 184.73, and we have only one member, so this total moment should be carried by this member, but distribution factor at this point is 0, so balance moment at this point will be 0. And at joint B we have two moment, that is minus 178.6 and 210.4. Then what is the unbalanced moment at this point? If we sum algebraically these two moments, then we will get the unbalanced moment here, minus 178.6 plus 210.4, then we get 31.8. We get a positive value, that is clockwise moment. To balance this moment, balance this unbalanced moment, we need to apply a clockwise moment of same magnitude, that is we need to apply a minus 31.8 moment at this B joint, and this moment of minus 31.8 kilonewton meter will be carried out or will be distributed to these two members. Then what will be the portion of this member? Minus 31.8 times distribution factor of this moment, which is 0.46, and it will give us minus 31.8 times 0.46 minus 14.63. and at this point it will be minus 31.8 times 0.54, and it will be minus 17.17. Similarly, we need to distribute this moment of this joint. Here we have unbalanced moment, like here if we sum this moment algebraically, 199.1 plus 148.9, it will give us minus 50.2. that is, we have minus 50.2 moment, we need to apply plus 50.2 to balance this moment, and this plus 50.2 moment will be distributed between these two members, CV and CD. For CV member it will be multiplied by 0.6 because distribution factor for this member is 0.6, and it will give us 30.12. Here we have balanced moment 30.12, and for this member this 50.12 should be multiplied by 0.4. 12.05. and here we have only one moment and one member, and distribution factor is 1, that is 1.00. that is, all the moment will be carried by this member and will be in opposite direction, because we have minus 137.8, and to balance this member we need to apply plus 137.8. so this is our first cycle of moment distribution method. Sorry, this value will be 20.05. here I made a mistake in calculation, it will be 20.05. alright, this is our first cycle. Now we need to continue this cycle again and again until these values are very near to 0. that is, our next row will be carryover moment. We have found carryover factor as half. Then what is the carryover moment? This moment will be carried over at this point, and this moment will be carried over at this point. that is, half of this moment will be carried here, that is 0.0, and half of this moment will be minus, if we multiply this by 0.5, then we have minus 14.63. half of this value is minus 7.32. then half of this value will be given here, and this value will be given here. If we calculate, then we get half of this 30.12, it is 15.06, and half of this value minus 17.17, which is minus 8.59, and half of this value this 20.05, 10.03, and half of this value 137.8, which is 68.9. again we need to balance this moment in the same manner. Here we have done in this row, we need to balance this moment, which is balanced moment. Again, balancing moment of this moment will be 0.00 because distribution factor for this member is 0, and balance moment of this joint will be, here we have unbalanced moment. If we algebraically sum this two value, then we will get 15.06. so we need to apply minus 15.06, and minus 15.06 will be distributed between these two member, that is for this member minus 15.06 minus 15.06 times 0.46, because we have distribution factor 0.46, minus 6.93, and for this member we need to multiply it by 0.54. we have minus 8.13. and for C joint we have unbalanced moment minus 8.59 plus 68.9. we have unbalanced moment minus 60.31, and of this minus 60.31, 60% will be carried by this member, that is multiplied by 0.6, minus 36.2 and for this member minus 24.12. Again for this member this will be minus 10.03, because this moment will be carried fully by this member only and sign will be opposite to balance it. Here we have completed another cycle. Thus we have completed here cycle 1 and cycle 2, and we need to continue this cyclic process, that is carryover moment, balance moment, carryover moment, balance moment, until these values become very near to 0 or 0 to make it accurate. And if you continue this cycle, that is carryover moment and balance moment, then we will get some values 0 point something or very near to 0, and then our final moment, that is actual moment at AB, actual moment at BA, will be the summation of all this moment, that is from fixed end moments from this row. We need to sum all the moment algebraically to get the final moment. As for example, for this example I'm gonna write the final moment, that is distributing this moment. Basically if you make 5 or 6 cycle, then it is sufficient enough to get the final moment. And if you do this cycle again and again, basically for 5 or 6 cycle, then you will get values very near to 0. And if you sum all those values starting from here, fixed end moment, if you sum all those values algebraically, then you will get the final moment, which will be for AB member, final moment will be, I'm gonna just write the answer, that is after completing this table in the same manner and adding all the moments algebraically, the value I am gonna write just here, that is 84.73 plus this one plus this one plus this one plus this one, and so on, 178.26. This will be minus 191.8 MBC. It will be plus 191.8, because this BA moment and BC moment should be cancelled out by each other. There should not be any unbalanced moment, and you will finally get the answer MCV, that is this moment. It will be minus 214.1, and MCD, that is this moment, it will be plus 214.1, and moment at CD will be 0. If we sum this column, then we will get moment at CD, because this support is hinge, then moment at this support will be 0. Now this is our final moment. Now we know the moment at this point, this point, this point, this point. That is this statically indeterminate beam has now turned into a statically determinate beam. Now we can calculate support reaction at this different point by deassembling this member into free body diagram. As for example, if I make just one portion, now this member is statically determinate to us. If you wanna go for further calculation, that is support reaction at this point or at this different point, we can find it very easily by taking the free body diagram. As for example, if we consider this CD portion, then we have this type of load, uniform distributed load, point load, again point load, 75, 50, this load is 20 kilonewton per meter. These values are kilonewton and these values are kilonewton per meter, and we have the distance 2 meter, 2 meter, 2 meter, and we know the moment here at this point. We have just calculated this moment is MCD and this point moment is MDC. We have just calculated MCD equal to 214.1 and MDC equal to 0. That is, we know this moment 214.1 and this moment is 0. So we need to calculate the support reaction here. So we are considering the right portion of this C support, so we can write it support reaction at C1 and support reaction at D. So if we take moment at D, then you will get the support reaction at C, and if you take moment at C or make the summation of vertical force equal to 0, that is using a static equilibrium equation, we can also find the reaction at RD. As for example, if you want to find the support reaction at RC, then taking moment at D, summation of moment D equal to 0, considering clockwise direction at positive. You can consider any direction as positive as your convenience. So at this point, this moment will give a clockwise moment, which is RC1 times this distance is 6, and here already we have anticlockwise moment minus 214.1, and at the same time this 75 moment, this 75 load will give an anticlockwise moment, which is 75 times 4, and this 50 kilonewton will also give anticlockwise moment. That's why it will also be negative 50 into 2, and this uniformly distributed load will also give anticlockwise moment, which will be 20 into total distance is 6, that is 6 square by 2, and there is no moment at this point here, equal to 0. If we solve this equation for RC1, then you will get it. Here it is 162.35 kilonewton. This value is 162.35 kilonewton. Now making the sum of vertical force equal to 0, we get reaction at this point 82.7 kilonewton. Similarly, we if we make the free body of this span, then you will get a support reaction here and adding this reaction here and here, we get the support reaction of this, that is RC. It will be RC1 plus RC2. So this is the complete analysis of this statically indeterminate beam. So I hope you got the point, and this is the end of this video. Thank you for watching.